This is the Databricks Data Engineer podcast. Your Spark job spends most of its wall clock time doing something that isn't computing at all. It's the slowest part of almost every slow pipeline. It's the reason adding workers sometimes makes things worse, and you could probably name what triggers it without being able to say what actually happens inside it. By the end of this walk, you'll picture it as one thing you've stood in yourself, an airport baggage claim, and you'll know exactly why your next wide transformation crawls. It's the shuffle. So let me put you somewhere you've physically been. A plane lands, everyone files off, and now every single bag has to get to the right carousel so people can make their connecting flights. Simple, right? Except the bags didn't arrive sorted by where they're going. They arrived sorted by the plane they came in on. That's the whole problem in one image. The bags are here. They're just grouped by the wrong thing. That's your shuffle. Hold that picture, because we're going to live inside this airport for the next few minutes. Here's the thing it's easy to carry around. You treat the shuffle as a black box. Group by is slow. Join is slow. Something mysterious and expensive happens in the middle, and the reflex when it's slow is: this needs more compute. Throw a bigger cluster at it, more workers. And sometimes that helps, and sometimes it does nothing. And nobody can quite tell you why. So let's open the box. Because once you see what the airport is actually doing, the mystery collapses. There are 4 steps. The airport does them, and Spark does them, beat for beat. Step 1. Every bag gets tagged with its destination carousel. A handler looks at each bag, reads where it needs to end up, slaps a tag on it. In Spark, that's partitioning. Every row of your data gets looked at and assigned a destination based on its key. The thing you grouped by, the thing you joined on, that's the carousel number. Tag every row. Step 2. The bags get piled up by destination. All the carousel 3 bags in one pile, all the carousel 7 bags in another. That's sorting. And here's a detail that matters. The cart that holds a pile is only so big. When a pile won't fit, the overflow gets dropped on the floor and dealt with the slow way. In Spark, that floor is your disk. When the data for a destination won't fit in memory, it spills to disk. And disk is dramatically slower than memory. Remember the floor. We're coming back to it. Step 3. The carts drive across the tarmac to the right terminal. The bags physically move. This is the network. Spark is shipping partitions from one executor to another, across the wire, and the wire has a speed limit. This is the part that isn't your join, isn't your actual logic. Nobody's running your aggregation here. We're just moving boxes. Step 4. On the other side, each carousel reassembles its load, so passengers can grab their bags. That's the reduce side. The executor that owns carousel 3 reads in all the carousel 3 data that just arrived. And now, finally, it runs your actual join or your actual aggregation. So, tag, pile, haul, reassemble. Tag, pile, haul, reassemble. That's the sentence I want you carrying to your next slow job. The compute, the part you think of as the work, is basically just that last step. Everything before it is logistics. Make sense so far? Good, because here's where it gets good. Now let me show you the failures you've actually lived as airport scenes. Scene 1. One flight came in with 10,000 bags. Every other flight had 10, so one baggage handler is buried for hours at a single overloaded carousel, while every other handler is standing around with nothing to do. The terminal isn't short on staff. It's that all the work piled onto one person. That's skew. One key has way more data than the rest. One task runs for an hour while the others finished ages ago, and your whole job waits on that one straggler. Scene 2. Someone decided to be safe and opened 1,000 carousels for a flight with barely any bags. Now you've got 1,000 carousels each holding 3 bags. And the overhead of spinning up each carousel, staffing it, running it, dwarfs the actual bags in it. That's too many partitions. The bookkeeping costs more than the work. Scene 3, the opposite. Way too few carousels, each one buried, bags overflowing onto the floor constantly. That's too few partitions, and that floor, remember the floor, that's heavy spill to disk. The slow path, over and over. Here's the move that breaks what you thought you knew. You're standing in this terminal, watching one carousel buried under 10,000 bags. What do? The instinct, the thing the dashboard practically begs you to do, is hire more baggage handlers, scale up the cluster, add workers. And it does nothing. Stay with that, because this is the whole episode. More handlers don't help when the bottleneck is the single overloaded carousel. The bags still have to come off that one belt. More handlers don't help when the bottleneck is the one road across the tarmac. There's still one road. You can hire every handler in the state, and the 10,000 bag carousel is still going to take just as long, because the problem was never how fast anyone works. You're probably thinking, okay, but my cluster genuinely was undersized sometimes, and adding nodes did help. Sure, when the work is evenly spread and every handler has a fair pile. More handlers absolutely finishes faster. That's the case where compute is the bottleneck. But that's not why most shuffles are slow. Most slow shuffles are slow because of how the bags are distributed, not how many people are carrying them. Skew, partition count, the haul across the wire. The bottleneck isn't the computing. It's the move. That's the reframe. Spark slowness in a wide transformation is usually a logistics problem wearing a compute costume. And you've been paying for more handlers to solve a problem that more handlers can't touch. Now, before you go reaching for the partition count by hand, here's the thing. Modern Spark already does some of this for you. On Databricks, adaptive query execution runs by default, and it'll quietly merge those 1,000 tiny carousels back into sensible ones, and it'll even take the overloaded carousel in a skewed join and split its load across a few. So it handles a good chunk of the small partition mess and the skewed join case on its own. It doesn't make tuning disappear, and it can't fix bad keys or rescue you from a join that should have been a broadcast. But it does mean the move isn't go set the partition count. The move is go find out where the bags are actually piling up, and then decide. So what do you do with that? Here's the diagnostic, and it's 2 questions you carry into the Spark UI instead of carrying your credit card to the cluster settings. First question, find the overloaded carousel. Open the stage that's slow and look at the tasks. If almost all of them finished and 1 or 2 are still grinding away, you've got skew. 1 carousel, 10,000 bags. The fix lives in the data, in how the keys are spread, not in the cluster size. Adding nodes leaves that one task exactly as slow as it was. Second question, read the move, not the math. In that same stage view, look at shuffle read, shuffle write, and spill. Those 3 numbers are the bags being tagged, hauled, and dropped on the floor. If spill is large, your carousels are overflowing. That's the disk floor. And the answer is about partitioning, not horsepower. The number you've been staring at, processor utilization, is the handlers. And for a slow shuffle, that's almost never the thing that's actually stuck. Find the overloaded carousel. Read the move, not the math. That's the whole toolkit. And here's why the design even works this way. Because you might be wondering why Spark would ever choose to drag everything across the network. It's not a flaw. It's the only honest way to answer the question you asked. If you want every matching key in the same place, and the matching keys arrived scattered across 100 machines, somebody has to do the moving. The shuffle is Spark being honest that the bags came in sorted by the wrong thing, and the only way to group them by the right thing is to physically move them. The slowness isn't a bug in the engine. It's the cost of the question. That's what I've got for you today. So here's what I want you to carry to your next slow join. Not the cluster's too small. That's the handler reflex. The real question is, which carousel is buried? And is this actually my join running? Or am I just paying to move bags? The shuffle is baggage claim. Tag, pile, haul, reassemble. And the bottleneck is almost never the people. It's the move. And it's a small shift in how you talk about your own pipelines. But it's the senior one. The junior version is, it's slow, let's add nodes. The senior version is, let me check the shuffle before I touch the cluster. Sometimes the cluster genuinely is the problem, and you scale it, but you check first. One of those reaches for the credit card by reflex. The other is an engineer who knows where the time actually goes. If this gave you a way to finally picture the shuffle, send it to the engineer on your team who resizes the cluster every time a job runs long. They're paying for handlers to fix a carousel. See you next time.